Hey guys, Mr. Mises here, and here we go. The last lesson in BC Calculus. We're talking about calculus of vector-valued functions. So I'm going to talk about some vectors here and taking some. If I keep looking up, it's because people just finished and making sure there's nobody coming in my room. We are talking about some calculus on vectors. Really not too bad. It's a lot like the parametric equations. So let's get into it. All right. So turn my screen this way. So the position vector, we define our position vector as x sub t and y sub t. All right, so it's basically a vector with respect to time. All right, and this gives a location of any object, as long as we're using that object in terms of vectors. Now the speed of that vector, or first of all, let's talk about the velocity vector. The velocity vector is, well, what do you think? Well, we're going to take the derivative of each of those. So it's x prime of t and y prime of t. Right? And if we're looking for the speed, we're talking about the magnitude of the velocity vector. So the magnitude, zoom this back in here, the magnitude of the velocity vector is going to be, and I'm going to put that in terms of t, is going to be the square root of the derivative of t of the x component squared plus the derivative of the y component squared. It's pretty easy, right? That should hopefully make sense. The acceleration vector, well, what do you think? What's the acceleration? The acceleration is derivative of velocity. So it's going to be the second derivative of the position of x and the second derivative of the y component. The distance, the total distance traveled, is going to be the integral of the position vector from a to b, so some values of a to b. Now, we're talking about the position, so we're looking at a magnitude, so we're going to take the square root of x sub t prime squared plus y sub t prime squared dt. So remember, distance traveled is going to be the integral of our velocity. All right, so when is the particle at rest? The particle's at rest when the velocity is 0. So when the velocity vector has a 0 x component and a 0 y component, then the object is going to be at rest. Okay, so let's take a look at using all of these things in a few examples. Oops. All right, so my first example, and I'm going to do one example on this video, and then I'm going to do the second example on another video, just to split the videos apart, all right? So given the position vector 3t squared and t cubed minus 3t squared plus 4, remember that the position vector is because this thing is moving in, the vector is x and y components, and this thing is moving in the x and y plane, right? So let's go ahead and graph the path of the particle on the interval from 0 to 2. Now, we treat these a lot like they're parametric. So it's similar to parametrically defined situations. So we're going to first start with 0. We're going to plug 0 in, and we're going to get our initial spot. So we plug 0 and we're going to get 0, 4. So 0, 4 is going to be here. And then we're going to plug 2 in, and that's going to give us 2 squared. It's going to give us 12. So again, we're plugging in 2 here. And so that's going to give us 12 comma 0. So 12 comma 0 is here, and so then we're going to graph that. And we probably want to find a value in the middle here. If I put in 3, 3 squared is 9 is 12. Okay, so that's going to be, sorry, not 3. Going to go like this. All right. Let's go and put 1 in. So we're going to go like 0, 1, 2. So when this is t, when t equals 0, we're going to get the point 0, 4. When t equals 1, we're going to get the point 3, comma 2. And then when we put 2 in, we're going to get 12, 0. So 3, 2 is going to be 1, 2, 3, 1, 2. Oh, so I was a little bit off there on my line, or on my. It looks like it's going to be a curve. It's going to curve like this, And we're going to put arrows this way because that's the way it's going, right? T is 0 starts here, and then 2 is there. The velocity vector at time t equals 1. So we're looking for the velocity vector. So we have the position vector. So we're just going to take the derivative of each of these. So we got 6t and 3t squared minus 6t. So there's my velocity vector. I want that at t equals 1. So I'm going to get 6 comma negative 3. And that's it. All right, so not too bad. The speed. Now the speed is the magnitude of the velocity vector. So we want the magnitude of the velocity vector, which is going to be square root of 6 squared plus negative 3 squared, which is going to give me the square root of 45. All right, that's it. Okay, so a lot of these things, again, we're just using the same techniques as we did before, only we're separating into two components. The distance traveled between 0 and 3. So the total distance is the integral from 0 to 3 of my square root of 6t squared of the velocity. This is the square root of the velocity squared, right? So the square root, the velocity was 6t squared plus 3t squared minus 6t squared dt. All right, and we're just going to go and enter that in the calculator. We're going to get 28.583. We don't really have a distance, so I'm just going to put units. Okay. At the time when the particle is at rest. Now we know the particle is at rest when v sub t is equal to 0, comma 0, right? So all we have to really do is take this this one right here, 6t set equal to 0. So 6t equals 0, so t equals 0. Now we are going to want to check the other one as well. So we're going to check this one here, right there, and we're going to set both of them equal to 0. And we're going to get 3t, factor out the 3t, and we're going to get t equals 0 and t equals 2. All right, so the particle at time is at rest. We're going to get t equals 0. All right. And at t equals 2, it's not at rest because when I plug 2 back in to my velocity, v sub 2 is going to be 12, comma 0. Now that's not when it's at rest. In order for it to be at rest, both of these have to be 0. So the only time that both of them are 0 is at t equals 0. So 2 is not really a place where the velocity is going to be equal to 0 or the particles at rest. Okay, so you still gotta check both of them, but remember that only one of them in that case is going to work. So we're looking for the acceleration vector. The acceleration vector is going to be the derivative of each of the velocity components. So I'm going to have 6 and 6t minus 6, and I want at 2, so I'm going to have 6 and 6, and that's my acceleration at 2. All right, so let's do the last one here. The direction of the particle at time t equals 1 and when t equals 2. All right, so the first thing we need to do is find the position vector at 1. And so we're going to plug in 1 into our original vector here. All right, so we're going to get 3, comma 2. And I believe that I found that out. Okay, that was right there. Okay, so then what we're going to do is we're going to find the direction. Theta equals the inverse tangent of y over x. And that is about 0.58. Okay, that 8 looks silly, guys. 8 to 8. All right, and that's in radians, by the way. So this is when t equals 1. What about when t equals 2? Well, s of 2 is going to be 12, comma 0, and we figured that out earlier. So the theta is the inverse tangent of y over x, which is the inverse tangent of 0, and the inverse tangent of 0 is just 0. So 0 radians. And that makes sense because 12, 0 is on the x-axis, and that angle is 0. All right, so there you go, guys. Here is some calculus of some vector-valued functions. That's my first example. I have another video that has example number 2. So we'll see you then, and that'll be the last video, really, of BC Calc. Catch you guys later. Bye.